welcome to this video. We're going to learn about wave reflection, wave interference, and standing waves. So far we've looked at this type of wave. You see crests, they're moving across, troughs, they're moving across the medium, and there's no end to the medium. The string just goes out the window forever. Now what we're going to do is look at what happens when we have a fixed end. Look at this very last particle. It's been clamped down so that it cannot move up, it cannot move down. So it's not free to be displaced. If we take a pulse and we send it through, then what happens to the pulse when it reaches this end? You can probably guess it's going to bounce back. But something else happens. See that? Now let's try the exact same thing, but this time we're going to use a loose end. That means this particle at the very end, is attached to a loop that can move up and down. So this particle is free to move. It's not fixed in place like before. Let's send a pulse through. Do you see what happens? When we hit the loose end, the wave doesn't flip upside down. But when we bounce off of the fixed end, the wave flips to the bottom side. What did we see? When a wave reaches a boundary, it reflects, and it bounces off, it goes the other way. So it reflects back the other way. If the end is fixed, right, then that term means the particle at the end is not free to move. Isn't free to move. So the particle cannot be displaced. And then we said also, if the end is called free, what does that mean? Well, if the end is free, then the particle at that end is free to move. So it can be displaced. At a fixed end, what happens to the reflection? Well, the wave is inverted, which means flipped upside down. And at the free end, what happens? The wave isn't inverted. So let's draw that. We've got a wave coming in, and let's say the wave looks like this. And it's moving to the right toward this fixed end. And so what's going to happen? Well, we know that if it's a fixed end, the wave will be inverted. That's what this says. Okay. But the question for us is it, when it gets inverted, is it going to flip upside down like this? Or is it going to flip upside down like this? Which one will occur? Let's test it out. Okay, let's test it out. I've got a wave going toward a fixed end. It reflects and inverts, and look at that. This steep edge is what reflects first, and it reflects again, and we still have that steep edge out front leading the way. And it reflects again, and the steep edge is out front, and this shallower edge always trails behind. So what did we say? We said, well, if the steep edge is leading the way, then when it reflects back the other way, we still have that same steeper edge. The same leading edge exists. So this is the picture that we get. Let's move this over. That's what the reflection looks like. Alright, give it a shot. Let's say we've got something like this. No, let's change it. Let's say we've got something like, yeah, like this. Here's a wave moving to the right toward a loose end. Let me draw my loose end like this. Right. We know the wave is not inverted. Oops. The wave is not inverted. And so when it hits the end here, it's not going to flip down to the bottom, it's going to stay on top. But you need this leading edge, this shallow leading edge, you need it to still be leading down below. So go ahead and give it a shot. Draw that reflection. So draw the reflection below. Two waves can overlap. We can send two waves toward each other, and when they meet in the middle, they will interfere with each other. Interfere. So when we say that they interfere, that means a combination of the two is produced. We call that combination a resultant wave. And we can calculate the resultant. We can calculate the shape and what it looks like. Here's the trick. Whenever the two waves overlap, their individual displacements are what add together. Not amplitudes, not frequencies, not wavelengths. It's the displacements that add at any single point in space. So we're going to look at that. The fact that we can add displacements is called the principle of superposition. Super, all one word, superposition. So let me show you an example. Let's say we have a first square wave like this, and it's overlapping with, let's see, there's another wave coming toward it that looks like this. Here they are coming toward each other. This first one has some displacement, right? There's this displacement at that point, this displacement at that point, and here's the displacement at the far left point. The other one has some displacement. There's this displacement at that point, this displacement at that point, and here's the displacement at the far right. We have to add the displacements at every single point in space. So let me draw the string again. Here's my string, and I've got the two overlapping together now. So I have to draw the displacements at this point, the far left edge. Well, I've got that displacement, and I've got this little displacement to add as well. And then I've got the displacement at the middle point, at that location. So I draw this displacement, but I add the middle one from the triangle as well, which is a big displacement. Then I add this other far right displacement on the square wave with this far right displacement on the other wave. Oops. And it looks like this. So what's the shape, the resultant shape? Well, the wave is going to start out like this, like we've drawn, but then the string is displaced up a little farther, and then really far, and then back down to this. So that's what the wave shape will look like. Let's test this out. Got my square wave, my triangle. Here we go, they're about to overlap, and I'm going to go forward slowly. Look at this. Does it make a house like we expected? Right there. You can kind of see that up. There's the triangle stacked on top of the rectangle. Now, this is called constructive interference, and the reason is because the two displacements of the waves, right, so these displacements in purple and these in green, are on the same side of the center line. Or you could say, are both positive. Or you could say, have the same sign or direction. Right? That's what defines constructive interference. This is going to be the definition of constructive interference. Whenever the two displacements of the waves are on the same side of the center line, and the waves are interfering. Oops, let me fix direction. So here's a question for you. Here's a question. If I take two waves like this, which are both below the center line, does this count as constructive interference? Is this constructive? Let's see, and then we have this super wave that we make. because we're adding the purple displacements with the green. So they go all the way down to the bottom there. Is this constructive? Well, both displacements of the two waves, purple and green, are on the same side of the center. They're both below. So yes, this is constructive. There is another type of wave interference called destructive interference. Destructive interference is what occurs. This is what occurs when the two, let's say when the displacements of the two waves are on opposite sides of the center line. Right? And so let's draw that picture. You've got a wave with positive displacement, and then you've got a wave with negative displacement. Right? Here's the positive, here's the negative, and we'll say that they're the same width. What happens when they overlap? To find out, we're going to use our simulation. I'm going to send the first wave through, and then I'm going to send the second wave through. This first one's going to invert because it hits the fixed end. And get ready, we've got these two waves. They're about to overlap, and watch what happens. Do you see that? Let's increase the... yes. Okay, I'll go in slow motion this time so that we can take a close look. As time passes forward in slow motion, here we go, they overlap, and look at what happens. Very briefly, for one moment, they cancel each other out. But it doesn't stay that way. The waves just keep on moving as though they never interacted at all. So look, here's the, I'm going to follow this negative wave on the right side. It moves over to the left, and after it still moves to the left. Here it is, it's the same one. Now it's a positive wave, and after it interferes, it just keeps moving to the right. They don't bounce off each other. They don't reflect off each other. They just keep on moving through each other. But for a very brief moment, our wave is just a straight line. The string is just a straight line because we're adding positives with negatives, and we get right back to where we started. The displacement will be 0. Adding positive with negative, making the net displacement 0.